Using semiclassical methods to approach the vibrational integrals that we're going to encounter in spectroscopic calculations. We knew when we encountered the R-centroid approximation that something special was happening, that there was a kind of localization that is not supposed to happen in quantum mechanics when we learn about the incompatibility of knowing both coordinate and momentum. Yet somehow these integrals were accumulating in a narrow region of space, and it's telling you that there's a hint that there's some localization that's relevant for understanding these processes. Okay, so in all of spectroscopy, we're always evaluating matrix elements, and these matrices always are expressed as a product of three factors. The electronic factor, which is mostly a radial integral. The angular part of the electronic factor is kind of an angular momentum integral and can be partitioned off because it's evaluable exactly. Then there's the nuclear radial integral. And then there's the nuclear angular integral, which is always just a number that you can look up by doing angular momentum algebra. So I should provide lecture notes. And you don't have this, and you don't have this, but Sirhan probably does. What did you have?
Oh, well, you can give me that after you.
Okay, you're not on the list.
I didn't have time.
Okay. All right. So we are always going to evaluate these matrix elements as a product of, or a sequence of three integrals. And so we have two basis functions, which I'm going to write in a sort of case A-like way. Okay, so we have these basis functions, which are eigenfunctions of some H0. So we've chosen to put certain terms of the total Hamiltonian into this H0. And this H0 defines a basis set. In other words, these are eigenfunctions of H0. There are no off-diagonal elements of H0. And we are free to choose which terms we put into H0. For example, the spin orbit Hamiltonian is some radial integral Li dot Si sum over electrons. That's a kind of inconvenient operator. This is actually a simplification already, but it's a kind of inconvenient operator, and you can simplify it to A, LZ, SC plus other stuff. And usually this gets put into H0, and this other stuff, which causes off-diagonal matrix elements between states of different lambda or S, those are saved for H1. So it's not even that we put all of H0, all of spin orbit into H0. Or we might not want to put this in there, because that would make it difficult to have a case B Hamiltonian. So, and in the rotational Hamiltonian, we have various terms. We could write the rotational Hamiltonian as B J minus L minus S squared, or we could write it as B N minus L squared, or we could write it as B N plus where this is the angular momentum of the bare ion. So there are a whole bunch of things you could use. These are true, but J is gone here. And certain coupling terms, I mean, here we have 3 diagonal terms and 2 cross terms, and 3 cross terms. Here we have 2 diagonal terms and 1 cross term. And so one can make all sorts of choices of what goes into H0. And some of those are dictated by convenience, and some of them are dictated by some expectation of what the molecule is going to be behaving like. Okay, so we have an H0. Jeff, I have notes for you. Okay. So, in order to be honest, we have to evaluate matrix elements of what we left out. So this is all of the terms in the Hamiltonian we didn't include in H0, which is where it becomes interesting. And this is, so we have an off-diagonal matrix element. And so we're going to have, we write this out. I should have done this in an earlier lecture because I think it would have made things a little more transparent to see the matrix element expressed or reduced in 3 steps to the number that appears in the Hamiltonian matrix. So we have V1, then we have E1, then we have some operator which has R and maybe R dependence. Then we have E2, D2. So this is where all of the radial and none of the angular stuff comes in. And then we have lambda 1, S1, sigma 1, omega 1, J1, M1. And then we have some other operator, which is purely angular. And then omega 2, J2, M2, lambda 2, S2, sigma 2. And I think that's it. Okay, and so this is an angular integral, it's true. This is a radial integral, and there isn't any algebra here. You just have to do a numerical integration, or 2 numerical integrations. So in the context of the Born-Oppenheimer approximation, this becomes some function, 1, 2 of R, operator, well, and then we calculate the vibrational integral of that, and then this whole thing becomes operator 1, 2, evaluated at V1, V2, at the R centroid. Okay, so now this is just a number. And it's a number that's telling you about some electronic property sampled at a particular point. And one of the things you discover when you play with these things is that almost no matter what you do, you're always sampling this property at the same point. And so it's really hard to determine experimentally, from experimentally easily observable quantities, how an electronic property actually depends on R because of some interesting and convenient facts. Okay, which we'll sort of touch on today.
Would
So-
you ever do like a small expansion, like a Gaussian type of expansion around the R bar and actually put in kind of a width to the distribution? Would there ever be a scenario where you would do that?
Well, I mean, you normally think of this as a linear function of R. And so you have a constant term in it and a first derivative term. And I mean, what you suggest is a perfectly reasonable thing, but it's actually going in the wrong direction. I'll show you how we can systematically vary our R in what kind of experiments. I'll try to remember to do that, okay? So, well, maybe I should just jump ahead. Suppose we have two potential curves that cross. Okay, and we're observing energy levels which accidentally are near each other. Because in our spectrum, we see these perturbations, and those could only be caused by energy levels that are at about the same energies in the two states. And it turns out that the value of R that gets sampled is always where these two curves cross. Now, if you could observe some kind of radial integral, sample this property between levels that are not near degenerate, perhaps by causing a transition, then what you do in order to calculate the overlap integral is to displace the curves up so that the levels are at the same integral, the same energy. And that moves the stationary phase point. So, I shouldn't have done this now. I think it really, it would be better if it came where I planned to talk about it in the lecture. But, for example, perturbations are always between levels that are at the same energy. And so they're almost always sampling the same stationary phase point. Transitions, Frank-Condon factors, are always sampling vibrational overlaps between one lower state and different levels of the upper state. And that results in causing, since if you visualize the calculation as shifting the curves up so that the vibrational levels are at the same energy, that systematically moves the intersection point. And that leads to the, as you follow a long progression of vibrational transitions, the transition moment is sampled at a systematically varied R centroid. And that variation in the R centroid is roughly proportional to the wave number of the transition. So for transitions, you can get the dependence of the transition moment as a function of R. But for perturbations, you can't. But there are these Van Vleck transformed quantities that lead to some fine structure. And those involve summing over states that are far away. And so they provide a little bit of information about the dependence of some electronic quantity on internuclear distance. So this may have been more detailed than you wanted, and it may have been in a package that is not understandable yet, but I tried to answer your question. Is that okay?
Well.
Shall we proceed? Okay. So, what I forgot to put in is this. So we're sampling this electronic quantity, and we have always this vibrational overlap factor. So we have a vibrational overlap factor, which we're going to want to calculate. We may want to calculate this, but if we know something about the curves, we know that. And then these integrals are just given to us by using angular momentum matrix elements. There's no radial dependence here. So if you know this, and you know this, then from the observed matrix element, you get this electronic factor sampled at the known internuclear distance. Okay? Okay. So in spectrum, we often care about R-dependent electronic factors. That's one of the products of our work. I mean, one of the R-dependent electronic factors is just the potential energy curve. We want to know about that. We want to know about molecular constants and how they vary with R. How does the spin orbit vary with R? Why does it vary with R? Because the electronic configuration is changing with R. If we have a deep understanding of what goes into this, we can learn a huge amount about how the spectrum samples R-dependent electronic factors. We can develop a classical mechanical-like picture of how the dynamics is occurring. Where is the coupling happening in space? When does it occur in time? Why does it occur? What enables molecules to have radiationless transitions from one electronic state to another? How do processes that aren't supposed to happen in H0, how do they happen? Where do they happen? What are we allowed to learn? Okay, so the purpose of this lecture is to focus on what we can get from this. Now, some people would say, well, why bother? If we know the potential energy curves, we can always calculate this numerically, and we can always calculate it accurately. But suppose we don't know the potential curves, or suppose we don't know anything about the electronic couplings. Well, then we don't know what to do with the information here. And so I want to show you how we can extract information about the positions of potential curves, the slopes of the potential curves at certain points, and the magnitudes of couplings, and what determines them. Okay, so this is going to be a lecture on semiclassical quantum mechanics, or at least a specific application of it. And this is not taught generally in chemistry quantum mechanics classes. We focus on just evaluating integrals exactly because we can do it. But the hard thing is to go from what we can do to what it tells us. And semi-classical quantum mechanics really enables you to make microscopic interpretations. That's what I hope to do. Okay. So what are the essential differences between quantum mechanics and classical mechanics? Well, in quantum mechanics we have the uncertainty principle. And it says that you cannot think about something like x of t, p of t. You can't imagine describing a trajectory. You need notes too. But in classical mechanics, we get all of our insights from trajectories. We follow something, and we know that at some special point in space or time, something dramatic occurs. That if you had motion on some kind of a potential curve, the system would be going back and forth, and then all of a sudden, at some point, it would find itself moving on this curve if there was some kind of coupling. I mean, you can think of two coupled oscillators. You can think of riding in a car, and the wheels aren't quite in alignment, and at some critical velocity, you start building up a resonance, and all of a sudden the car falls apart. And it's very much like that because of a resonance or because of some particular localized phenomenon, a dramatic thing occurs. And we know this happens in quantum mechanics, but we don't allow ourselves to think about localization. Okay, we also have wave functions that oscillate. So there are nodes, and we're talking about amplitudes rather than probabilities. And so there's interference effects, and there are some complications that we know are outside of classical mechanics. But a lot of these complications can be made to go away. So what we want to do is build up a wave function which is constructed out of quantities we know from classical mechanics. And these wave functions will have the absolute minimum of stuff that allows them to be quantum mechanical. But everything in them is connected to classical mechanics. Okay, well, we have this interesting relationship that the de Broglie wavelength is h over p. So this is the expectation value of the momentum, or this is, you know, what is this really? Well, we can say that this is the classical momentum evaluated at some value of the coordinate. And then the wavelength is varying with r. And classically, P of r is given, well, we have the kinetic energy minus V of r is p squared over 2 times the reduced mass. So we can get P of r is equal to 2 mu times E minus V of r. So this is the classical momentum at r. It's not the quantum mechanical momentum, but it's a function that is related to the quantum mechanical momentum, or it's related to the momentum, or it's just a function, and it's classical. So we have the energy, we know that. We have the potential energy curve, which we want to know, and we have this. So we could then use this to calculate the spacing between successive nodes. And this is absolutely correct. If the kinetic energy is varying rapidly with r, then we have to be a little bit more careful, because we need to evaluate an integral over P of r dr, and we have to accumulate pi of phase before we have the next node. But if it's not changing, we can be really naive and just say, well, we're going to evaluate the de Broglie wavelength at a particular region of space, and that's telling us how far the nodes are apart, or what the spatial oscillation frequency of the wave function is. And it's really accurate. And now that's the quantum mechanics. Okay, so we have also the wave function. Well, this is some probability distribution. This is not the momentum anymore, this is some probability. Okay, and so, well, what is the probability of finding a system classically in a particular region of space? Well, it's proportional to 1 over the velocity. Right? If a system is moving through space, it's going to spend a certain time at r, and that will be 1 over the velocity. So we know that psi of r is going to have to be proportional to the classical momentum 1 over the square root of the classical momentum. And that's the envelope. So now we have an envelope which is r dependent, and for the most part this is correct. There are cases, if p of r is 0, this would be infinite, and we know that's going to be troublesome because the wave function is never going to be infinite. And the classical momentum is 0 at a turning point. And we're really interested in turning points, so that there is a fundamental problem here. Okay, so we have an envelope, and then we have a wave function that's going to be oscillatory. And how does it oscillate? Well, it's going to oscillate to pi r over lambda of r, right? That's what we mean by a wavelength. So this is telling us how the wave function is going to oscillate. So this is pretty close to the WKB wave function. The only thing that's missing is this doesn't accumulate phase properly because it's acting, it's telling you the local oscillations. So you need to accumulate phase if there are going to be interference effects, the phase has to be right. But this is easily fixed. So what is this? Well, this is h over p. So we have r times p. R times p has dimension of action, and so we have sine of r times p of r over h bar. Sine, okay, that's all right. And since we know what p of r is, we can plug in what the energy dependence. We can write this function. So everyone who's taken 561 should be bothered by this, because it's drummed into you that you can't know the momentum and the position. But this is only the classical momentum. It's nothing quantum mechanically. It just is something that enables you to have the right phase, the right oscillations. Okay, the WKB wave function, which we derive by doing a kind of power series expansion of the Schrodinger equation of powers of h bar, or 1 over h bar, and just keeping the lowest, the lowest power we can. Anyway, it has this form. Some normalization constant, p of r over h bar, 1 over square, sine phi of r plus pi over 4. So this is the accumulating phase. Phi of r is integral from a turning point to r of p of r dr. So this is exactly what we had here, except now we're treating the phase as well as the oscillations. And this pi over 4 is a special boundary condition that enables you to cross through this singularity in the wave function at the turning point and join up with functions that that behave properly in the non-classical region. In other words, they decay exponentially to 0 at infinity. So this is what you need. It's derived by a clever splicing of the WKB wave function onto a wave function that works near the turning point, which is an airy function. And so this is quite rigorous. And so even though the wave function, the WKB wave function, is not valid near a turning point, it's valid everywhere else. And so this is in the classically bound region, and this is the right phase. So now what we've done is we've got in the wave function the momentum. We've got, and this momentum depends on the energy. We've got the energy dependence. We've got the spatial dependence. So we've got the oscillations. We know what the oscillation frequency is. We know what the envelope is. We know how they depend on energy. And so you don't have to solve any Schrödinger equation. All you have to do is say, I want to know about the wave function here. And I know what determines the essential features of the wave function here. They are the amplitude from the envelope, the spatial oscillation frequency from P of E, and the phase, which is gotten by this phase integral. And normally you don't need this. That's only when you're really trying to do something accurately or when you're trying to understand an interference effect. But often this is an extra complexity. But it's not solving a Schrödinger equation. It's an integral over an explicitly known function if you know V of R. And if you don't, this is one of the ways how you get it. Okay. So now we're ready to deal with this kind of a problem. So suppose we have two electronic states and they have potential curves that are like this. And there is some coupling term between these electronic states that means that these two zero-order levels are going to be not eigenstates. The system, if initially prepared in a zero-order level like this, is going to end up going back and forth between these two zero-order levels. Or if we're working in the frequency domain, the eigenstates wouldn't be in here and here, they'd be pushed apart a little bit. And the eigenstates would be a mixture of these two levels. If we made a wave packet, the wave packet might start moving along here and going back and suddenly appearing over here. And I made it appear suddenly over here by jumping at this special point. That's in fact what happens. Amplitude leaks from one to the other at this stationary phase point. So what we want to do is understand the overlap integral, and in particular, well, the overlap integral is an integral of R from 0, because at 0, you can't have an integral through distance less than 0. So 0 to infinity of chi of V1 of R, chi of V2 of R, dr. Now, vibrational wave functions are real. So we don't have to play games with complex conjugation. We could be evaluating the integral of some function of R, and the same argument applies. It doesn't, unless this function of R is really kinky, it doesn't care. So on this plot of energy versus R, where these things cross, we have R, C, and E. So the two curves intersect at a particular energy, and they intersect at a particular R. And those two quantities are going to play a critical role in everything we do. Okay. First thing is, suppose we ask how this integral accumulates as we integrate over R. In other words, we have 0 to R, not to infinity, of chi v1 of R prime, chi v2 of R prime, dr prime. Okay, this is telling us how the integral accumulates. If we set R equal infinity, then it will be the value of the overlap interval. And what you see, generally, is the integral accumulates like this. It's oscillating around 0, and then it jumps up to some value, and it oscillates around the final value. So it's telling you that something happened at this special internuclear distance. And what is that internuclear distance? It's RC. And why does this happen? Because the wave function on this potential and the wave function on this potential at RC have the same classical momentum. They have the same de Broglie wavelength. That this function, which is a product of two rapidly oscillating functions, this function stops oscillating at RC because the two functions oscillate at the same frequency. That's the stationary phase condition. And the integral can be said to have a value which is determined by chi 1 of RC, chi 2 of RC. So that's the amplitude right at the crossing, times delta R stationary phase. The length of the stationary phase region. And what is that? That's how far you can go before these two wave functions accumulate pi phase difference. Why would they accumulate pi phase difference? The potentials at RC have different first derivatives. The derivative determines how the phase accumulates. And so this is basically related to the derivative of potential 1, derivative of potential 2, evaluated at RC. So we have something from the envelope and something from the phase accumulation. So these are classical quantities. These are the quantities we often want to know. We'd like to know EC, RC, and the difference in the derivatives at RC. And by looking at the systematics of the vibrational overlap integrals, we can determine all of these quantities. So the stuff we want to know is explicitly embedded in the integral that we might evaluate numerically. But if we evaluate it semiclassically, then the connections are all exposed. And so you know exactly what to do, rather than doing some elaborate numerical study to find out the sensitivity of some potential series of observations on what you want to measure. So here is where you really do it, get insight. Instead of trying to get insight by numerical explorations, you say, I know what the important factors are, and how do I arrange my experiment to expose those important factors? Or how do I do the calculations that I need to do rather than all conceivable calculations in order to expose what might be relevant to the experimentalists? This is kind of a revolutionary idea because we're not used to trying to extract from an exact numerical result insight. We're not used to analytic theory anymore. We're used to numerical analysis. But often having physical insight can direct you to the specific class of calculation or the specific class of experiment that will actually determine something that nobody else knows how to do. Because we all know from working in the lab that everything we try to do, even if your research supervisor tells you it's trivial, takes a long time. And so you might as well do the right thing first rather than something else, because whatever it is you do first is pretty much what you're going to be doing forever. And so having insight is a good thing. And similarly for calculations, although I haven't had the experience of being told what calculations to do, but I'm sure that it's the same sort of thing. Okay, so now let me simplify this equation. Whenever I give a lecture, my entire body gets covered with chalk. And I remember watching E.B. Wilson lecture when I was a graduate student. And he would stand there, he would be dressed immaculately, he would wear a jacket and tie, and he would hold the chalk, and he would actually spin it in his fingers, and at the end of a lecture, you could not find a particle of chalk on him. It seemed that way anyway. And I just wonder, how did he do that? But anyway, okay. Okay, so I want to return to this product of amplitudes. And how would I determine this product of amplitudes? Well, the product of amplitudes is given by a time over a period. So the amplitude is given, since we want a product of two amplitudes, we're going to calculate these two amplitudes. What is it? This is the time it takes for the particle to move through the stationary phase region. Okay, and so here is the stationary phase region, and so we pick an energy, we know a momentum, we know a velocity. Okay, we know the length of the stationary phase region. So if we make the approximation that the velocity is constant over the entire stationary phase region, and since the two levels are at the same energy above the stationary phase, the velocity in both is the same. So T1 is just our stationary phase, the length of the stationary phase region, over the velocity at the our central at the crossing point, and we know what that is. Okay, and what's the period? Well, how long does it take for the system to go back and forth? Well, classically, that's given by the well, quantum mechanically, it's given by h over EV plus 1 minus EV minus 1 over 2. The average vibrational level spacing at V. And that's called omega bar V. Or, 1 over omega bar. Okay, and we can get this either, where do we get these two energy differences? Well, we might measure them. Or we might get them from the WKB quantization condition. which is P, E, or P, B of R, dr, from the left turning point at dB to the right turning point at dB is equal to h over 2 times b plus a half. It's basically saying that each vibrational wave function has v internal nodes. And you're just accumulating the phase from one turning point to the other. And this tells us where the vibrational levels are. So we can use this to find the v plus 1 and v minus 1 level energies and calculate this average omega. Or we can modify the WKB quantization condition to actually get the period directly. It's just taking a derivative of the integrand. And it's still a numerical, they're both numerical integrals. But they're not integrals of wave functions, they're integrals of a classical function. And so we can get the fraction of time in each oscillation period. System 1 is in the stationary phase region. Fraction of time in each oscillation period. System 2 is in the stationary phase region. The probability amplitude is the product of those. And so now we have a function. The length of the stationary phase region is determined by this difference of derivatives. We have this this amplitude at the stationary phase point, which is basically these factors. And I'm sorry, whether I'm walking back and forth. Okay, so basically we have now all of the stuff we need in terms of quantities like that we would use to describe the motion of a wave vector or motion of a classical particle. Now, suppose we have this problem. Suppose we have a bound state crossed by a repulsive state. So we would need to calculate the overlap between a bound state and a repulsive state. And there are different normalization schemes for bound states and repulsive states. So, but one trick is to say, okay, what the hell with this? Let's just make the repulsive state bound by building in an infinite wall at large r. So now the repulsive state has a very high density of vibrational levels, and we can find them. And we can find the vibrational period. We can find the amplitude in the stationary phase region using the same techniques for both. And so then what you care about is what is the interaction between the repulsive state and the bound state as a function of vibrational level of the bound state. That's an observable quantity. So if we were to plot the width of the bound vibrational level, or the quasi-bound vibrational level, versus V, what we would find is that the width is essentially 0 for a while, and then it goes up suddenly, and then it goes down. It might oscillate. It might, so there's going to be, as a function of V, the width, due to predissociation, will have a characteristic shape. And all of the features in this characteristic shape are related to the quantities we care about. EC, RC, difference of derivatives. Shape of the delta curve. Everything. And so, if you know the bound curve, and you can make some observations, this rapid onset is basically telling you that at this vibrational level, that's about the energy of the curve crossing. And then as it goes, how big it gets is related to the slope. When it starts to turn around is also related to the difference in the slope. And getting a node is a very sensitive thing, because in experimental spectroscopy, measuring absolute intensities or absolute quantities other than frequency is really hard. But getting a zero, even if you don't observe the zero, you see it's going down when it starts coming up, you know the zero is in between, and that tells you really well the quantity you want. So now what I've done is I've said, okay, there is this numerical integral that if you knew both of these curves well, you could calculate. But generally you know this and you don't know that. And so I've shown you how you can use the quantities you can measure to determine the shape of this curve accurately in this region of the crossing, which fortunately is the only region that you're sampling. So even if the coupling is strongly R-dependent, it doesn't matter, because the stationary phase condition is so strong that it picks out the value of the coupling function at that critical distance and almost doesn't care. And you can even prove that if it's varying linearly, it's completely independent of where you sample it. If it's varying quadratically, by going over a very wide range, you can begin to pick up that quadratic dependence. Okay, so all of the physical stuff is connected to what you can observe, and that's really neat. Now, I told you how you could calculate all of the relevant stuff, and I made a lot of gross approximations. In my book, there is a formula, V1 or VI, Vj, and you'll see that all of those things appear in the formula, but also with a little bit more rigor. Okay, so the vibrational overlap is given by 2 times h bar omega 1 bar, h bar omega 2 bar, and the reduced mass over h bar p of r crossing the v1 dr minus the v2 of r and r crossing. Okay, so this is, what are these? These are T1 and T2. This is the amplitude, right? Because the amplitude, the velocities are the same at the crossing point, so we get a square root of P from both, and this is the difference in derivatives. So all the good stuff is there. Okay, then we have square root, which I promised. And then we have the stuff to make it physically correct. We have psi of E, Airy function, minus psi of E. Okay, this is the phase vector. This is what I would like to leave out. But sometimes you need to know the phase at each of the stationary phase points, if there's more than one, because you get interference. So this is just keeping track of the accumulating phase. This integral is a product of two Airy functions. The integral of a product of two Airy functions is another Airy function, and so that's where that is. Okay, and so we have psi of E is, you know, this is needed because the argument of an Airy function is a little bit strange, and so, but this is the phase factor. So we have A2 to RC, P2 of H bar dr plus B1 RC P1 of R dr for H bar. So what you can see, this is the turning point of potential number 2. This is the turning point of potential number 1. We're just integrating the phase, we're just doing the phase integral from the turning point into the place where the two functions, where the integral accumulates. And so we're going to get the sign of the contribution to the integral from the stationary phase point at RC. So this part is a detail, but this is basically all the physics, or all the classical physics. And that's kind of neat. And I know of very few spectroscopists who worry about such things. They just make the measurements and say, well, some theorist is going to tell me what these mean. For my PhD thesis, I measured perturbation matrix elements, spin orbit and rotational perturbation matrix elements between two electronic states as a function of V. And I was able to show that the measured coupling terms were the product of a constant electronic factor times a vibrational overlap. So that was the first demonstration that one could use this expected separation of coupling matrix elements into a constant radial factor and a vibrational overlap. Just like you do for electronic transitions, where you have a Frank-Condon factor, which is an overlap squared, times an electronic factor. And then I used the same idea as a postdoc to get absolute vibrational numbering of dark states, states that you couldn't see by looking at the variation of the perturbation matrix elements with vibrational quantum number in the bright state. But I didn't know the semiclassical arguments. So I saw these oscillations, and I knew that the oscillations were, the zeros were really important. And the zeros really nailed the vibrational numbering. And then later on I figured out that, well, I could have approached this problem very differently. And, okay, so, suppose, and this is related to the question Dave asked last time, suppose you have kind of flabby potential for a very strong one. So you have a stationary phase point here, a stationary phase point here, a stationary phase point here. So the vibrational overlap would accumulate at 3 points, and the accumulation at these 3 points would each of the contributions could add either constructively or destructively, and you get into trouble. Well, as I've drawn it, if you're at low energy and you're sampling the interactions, this one is irrelevant. As I've drawn this, these two come in at about the same energy, and that would be the worst of all possible conditions. Normally, you get the turning on of an interaction associated with one stationary phase point, and then at somewhat higher energy you might see the appearance of another one. And that leads to complexities, but if you've got enough of a purchase on the problem from the first one, then this is not a big deal. That's just giving you another, you can undo the interference effect, and it's just giving you another value of the potential and its slope, which is useful. Okay. Classical mechanics, oh, we're going to finish early. So you can bring classical mechanics into quantum mechanics through the stationary phase or the semiclassical wave function. But you can also bring classical mechanics into quantum mechanics by making wave factors. These are particle-like states which are described in a purely quantum mechanical way, but they behave following your classical intuition about how a particle moves out of potential. But there are always these things about how does a particle get from one potential to another. Is it magic? Does it happen in some random probabilistic way, or does it happen at a particular location in space? And one of the pictures we have to describe these sorts of phenomena it's the Landau-Zener model. So we might start a wave packet here, and it would move back and forth. And when it goes through the region of this avoided crossing, the particle might stay on this curve, or it might jump to the other. And we have a nice theory that comes from our own experience driving too fast in a car. If you're going too fast and you have to make a right turn, you can't do it. You could roll the car. But if you go slowly, it's no problem. And so we have something that's related to the curvature here, and the gap, and the velocity. And those quantities in the diabatic picture are exactly the quantities we've been focusing on. The velocity, well, we've been talking about the velocity, right? We have the classical momentum. The gap, that's the coupling matrix element. In the diabatic picture, we have a difference in derivatives. When the difference in derivatives is large, it's really hard for the system to jump. When the difference in derivatives is small, then I'm sorry. When the difference in derivatives is large, it likes to jump. When the difference in derivatives is small, like here, it's hard for it to jump, because it can make this gentle curve. And so I'd like to be more explicit about the connection between the Landau-Zener model and the quantities in my semiclassical wave function. I know I can. That was going to be the last lecture. I'm not sure in a finite time I can do this more than in a hand-waving way. But I'll have something to say on Friday about some topic related to this. So that's all I have to say today. Are there questions? Yes?
When you say the difference in derivatives, do you mean the difference in derivatives for the lower potential energy curve on either side of the maximum, or do you mean the difference in derivative between the two curves on the same side?
Okay, when in the Landau-Zener picture, that's expressed in terms of non-crossing or adiabatic curves.
Okay.
The picture that I've been developing is diabatic crossing curves.
Okay.
The difference in derivatives for the diabatic crossing curves at the crossing is related to the curvature here and the gap, but how that works, I need a little more time to work out if I can. But the quantities I've identified in the semiclassical wave function are together related to the Landau-Zener crossing or non-crossing formula. All of the classical quantities are present, and that I would like to talk about, and maybe I don't know what else I'm going to talk about on Friday. Maybe it'll just be a bunch of loose ends. But I'll have something to say on Friday. But this semi-classical quantization, the semi-classical wave function, this was really what the whole series of lectures was